Okay, now we're going to clip the surface, but first we need to examine the publication, so we'll have exactly the same system if we want to, of course, compare the results. Okay, so as we can see in the publication, the MgO slab has diameters A and B, meaning the surface 16,8448 angstrom, which corresponds to 4 times the unit cell vector length, and the C length is 105280, which corresponds to some fractional thickness of the during the cleavage process. Okay, so let's try to recreate this system. We go to build, surface, cliff surface, cliff surface, cliff surface. The cleavage plane is 100. Okay, so let's set up 100. Okay. The fractional thickness, as you can see, corresponds to 2.5. That's exactly this 10.528. Now, as you can see, the blue box indicates the way how the crystal will be cleaved, and as you can see, the configuration of this box is that each side is a diagonal of the MgO crystal. Now, if we would stay with this configuration, then of course the size of our cleaved surface would never correspond to desired to 16,8448, right? Which is, again, it's exactly 4 times the unit cell. Okay, so we have to reorient the blue box. Okay, and this the orientation is defined by the surface vectors u and v. Okay, so we want to reorient the surface vectors from diagonal position into side position. Okay, so this one will be 0. This one will be 0. This one will be 1. This one will be 0, and there we go. Okay, and as you can see, the mesh length now is exactly 2.411, and we can clip the surface. Okay, so clip the surface. There we go. This is our system, and in order to again reproduce the system in the publication, we need the MgO slab. That size is 16.8448, which is again 4 times the system. So we will create a supercell out of the cell. I will store it in a separate document. Okay, I will name it. It's 4 times 4. Because it will correspond to the supercell, which is 4 times 4 the original cell. Okay, so let's copy it. Okay, so I'm going back to the original document. I press Ctrl C. Okay, to copy the whole system, I go to MgO, new MgO document. I press Ctrl V, and I copy my structure. Now the supercell. Okay, so I go to Build, Symmetry, supercell, and I choose 4 times 4. And that's my system. Okay, my system, I can check the lengths. Okay, everything looks good. That's my system, which is ready to proceed with the publication. Okay, however, in the publication, there is no mentioning about optimizing the size of the system. And to do this, we need to optimize. One could actually optimize this, the size of the surface and the thickness of the crystal according to the value that we're actually computing. And what we're computing is the bonding energy. Now, as you know, the problem with the size of the system is that because of periodic boundary conditions and electrostatic interactions, because electrostatic interactions are also periodic, that means that if we have a molecule here and the system is, if we have a molecule here, due to periodic boundary condition, the molecule will actually act as itself, so that the energy will be much greater than in reality. To overcome this problem, we use something which is called the cutoff distance. Okay, so the cutoff distance is a very simple idea that you can actually find it also in Material Studio options up here. And this cutoff distance is a distance, is a radius of the sphere where the electrostatic interactions are actually being computed. And in the situation where this we are outside of the sphere, the electrostatic interactions are simply neglected. So depending on the cutoff distance, that depends on the quality, as you can see, we need to adjust the size of the system so the molecule will not act on itself. Okay, and to do this, first we will create a couple unit cells with varying dimensions, and we'll calculate some value that shouldn't change with the size of the system. And one of those values is the bonding energy. Okay, so let's create 2 more structures. Oh, 3. Okay, and once again, I will copy each original clear surface to my new documents, and I will rename each document so it will indicate the size of my desired system. Okay, and within each document I will create a supercell corresponding to the desired size of the system. Okay, so in this case 2 by 2, in this case 3 by 3, and in this case 5 by 5. Now let's create our Manhattan molecule. Okay, so it's a simple carbon structure. 1, 2, 3, 4, 5, 6, 7. Yeah. 4, 5, 6, 7. I'll add hydrogens, clean it, and optimize it using Commons Force Script. Okay, so I'll add the job. And there we go. Okay. Now, in the next video, I will show you how to compute the bonding energy and how, using those values, how to choose appropriate size of the system.